This last one's a little bit more difficult because it's also tough to picture, because it's dealing with a hypothetical type case. And one of the things that students really have a problem with is when they say hydrogen-like, it means an atom that behaves and will obey Bohr's formulas, but it doesn't have the same values for R1, and it doesn't have the same values for E1, and you can't use Rydberg's constant. So that's what the real trick with this is. Whenever they refer to a hypothetical hydrogen-like atom, that means you have to figure out what the initial energy level would be. You can't just use the actual hydrogen values. So it's one way to ensure that you really have to use these formulas more than once. So because it's hypothetical, we know that the fourth value, n equals 4, so the energy level 4 is negative 1.10 electron volts. What we want to find out is two things. We want to find out the velocity at the second orbit. Well, for us to find out the velocity, we first of all have to figure out what E2 is. Energy of that level is going to be how much energy the electron has. So the trick with this is E1 is not negative 13.6. That would only be true if this was hydrogen. Because it's hydrogen-like, we go back to Bohr's formula and we say E4 is equal to E1 over 4 squared, but we need to find out what E1 is. E1 is equal to 16 times E4. Notice when you work this out, 16 times negative 1.10 electron volts, you don't get the exact values that were for hydrogen. What you get is something that is hypothetical, hydrogen-like, meaning it'll obey these formulas, but it won't have the same values. Hydrogen was negative 13.6. This is negative 17.6. So it's some other atom that can obey these formulas is really what it means. Now that I know what E1 is, now I can go and find out E2. E2 will be equal to E1 divided by n squared. E2 equals negative 17.6 electron volts divided by 2 squared. So E2 is going to equal to negative 4.4 electron volts. So what does this mean? Therefore, energy of the electron, I'm going to write this out, in orbit 2 equals 4.4 electron volts. So if this is the energy of the particle, we can then say that it's all kinetic because the electron has very little mass, so the potential energy is minimal. So the energy of the electron will be equal to 1/2 mv squared. Solve for the velocity. Well, 2ek divided by m square root equals velocity. We know this formula requires energy to be in joules, so it's 2 times 4.4 electron volts. The conversion is 1.60 times 10 to the negative 19, right, off your formula sheet. That's the elementary charge, joules per electron volt, divided by mass of the electron off my data sheet, 9.11 times 10 to the negative 31 kilograms, and take the square root of that answer. The velocity, punch this in, 2 times 4.4 times 1.6 to the exponent negative 19 divided by 9.11 exponent negative 31. Square root that answer and you get 1.24 times 10 to the 6 meters per second. Again, if you understand what these values should be, the velocities of the electrons in this level should be around 10 to the 5, actually shouldn't even say 10 to the 5, should be in the 10 to the 6 neighborhood, depending on how high or how low, depending on how close or how far away from the nucleus. It tends to travel a little faster the closer you get to the nucleus because the electric force is stronger, which you see in the video when you go there. This one, the trick with this, and this is one that always tends to throw students for a loop because it's tough to picture what does hypothetical hydrogen-like mean. What it means is you are allowed to use the formulas, but you're not allowed to use the constants. Rydberg's constant, that 1.10 times 10 to the 7, not allowed. Bohr's E1, negative 13.6, not allowed. R1 of 5.29 times 10 to the 11, not allowed. So you would be able to calculate those initial values using the formulas, but you can't use the constants that are for hydrogen specific. Remember, it's RH, Rydberg's constant for hydrogen. E1, electron volts for hydrogen. R1, for hydrogen. So when you get hypothetical hydrogen-like, you need to figure out those initial values of E1, R1, RH, then you're allowed to use the formulas.